Good afternoon, community members. Today, Ayush Gupta, and my colleague Ekaterina Dorzhieva will be presenting the project SwarmHawk self-sustaining multi-agent system for landing on moving platform through an agent supervision. Heterogeneous teams of mobile robots and UAVs are offering a substantial benefit in an autonomous exploration, inspection, and delivery. By 2028, the autonomous last mile delivery market is expected to exceed 51 billion US dollars from 8.7 billion US dollars in 2020. The growth of the autonomous last mile delivery market is led by development of aerial delivery drones. However, last mile delivery is to remote areas remains a challenge for companies across industries, whether it comes to cost or efficiency of the whole system. Meanwhile, multi-agent systems are still suffering from low adaptability to changes in external conditions. One of the most challenging tasks is swarm docking. Several researchers have been recently exploring the means to improve the robustness and accuracy of the UAV landing on moving platform. Some of them use control system for large swarms for landing on platform and predictive control for collision awareness in accordance with the outdoor real condition, but either they didn't take account the constraints of the dimensions of landing platform or the distance of for the safe landing. We propose SwarmHawk technology. The goal of this project is to have a robust collaboration between mobile robot and swarm of drones while landing on moving platform. The novelty of this project is multi-agent system with vision-based tracking and collision awareness for safe landing of UAV swarm on moving platform. The overall system consists of heterogeneous robots, which are swarm of drones and a mobile robot. The swarm of agents consist of Raspberry Pi camera, and a rotating mechanism allowing the camera to be used both horizontally and vertically depending on the task. For drones localization, Vicon V5 motion capture system is used. The Bitcase Crazy Flag of firmware was used to control the drones via ROS. The swarm can land on the platform switching between two scenarios of the vision-based tracking system, which are homogeneous swarm visual localization and leaders followers visual localization. The algorithm for the swarm control is shown here. The main loop runs the condition of successful landing of swarm of drones. While the swarm hasn't landed, the swarm operates in one of the two modes based on the availability of the camera feed from the swarm agents. In case of stable camera feed from the swarm agents, the swarm operates in homogeneous swarm mode, flying in triangular formation to land on the moving platform. The formation is being held as a virtual structure that can change its orientation based on the yaw angle of the target platform, thus landing safely using artificial potential field algorithm. In case of missing camera feed from one or more swarm agents, the swarm operates in leader-follower mode, where one drone with available camera feed assumes the position of the leader. The leader drone is selected from the agents with available camera feed based on the minimum of the cost function. The chosen cost function in this case is the Euclidean distance between the available agents and the position of the drone which lost the camera feed. After the leader drone is selected, the faulty drone will operate as a follower, where the leader drone can localize it and guide to land on the moving platform, avoiding collision with other swarm agents using artificial potential field. Artificial potential field is implemented as the sum of the two virtual potential fields, attraction and repulsion. The attraction potential field, which pulls the drone towards the target waypoint, is in the second equation. The potential is proportional to the square of the distance between the drone's current position and the target position, where zeta is the scaling factor which is tuned for each scenario. The repulsion potential pushes the drone away from the obstacles. In the third equation, the drone isn't affected by obstacles repulsion unless the drone is within the distance d0 from it. The shorter the distance rho between the drone and the obstacle, the higher the repulsion and vice versa. Thus, the drone can avoid collision with the obstacle. By calculating the artificial force acting on a drone from the combined potential, we can correct the drone trajectory to reach the target while avoiding collisions.
3 experiments were carried out on landing a swarm of drones on a static platform. the platform moving along a line, and the platform moving along a complex trajectory, rectangle. In the first two experiments, two options for drone control were considered. In the first case, the drones found the landing site using their cameras. In the second case, the movement of a swarm of drones was considered in an emergency case of a breakdown of one or more cameras. Then the landing site and the current position of the drones were tracked from the above by the camera of the leader drone. In the third experiment, the landing of the swarm in the leader-follower formation was evaluated with platform moving along a complex trajectory. For experiments, we used drones based on the Crazy Flip platform. On first one, we fixed a Raspberry Pi 4 with spy camera with servo motor that can rotate camera. The size of the landing platform was 45 by 57 centimeters. The beacon motion capture system was used to obtain the trajectory of the mobile platform and the desired landing points for the drones. All experiments were aimed at calculating the root mean squared error of landing. Each experiment for each case was carried out 5 times. Overall, 15 flight experiments were accomplished. In this experiment, the mobile robot is set to a stationary position, and the swarm of drones is launched. In the first case, a swarm of 3 drones lands on the platform receiving coordinates from image, processing on their cameras. In the second case, the cameras of 2 drones fail and 1 drone flies higher by 2 meters, and the camera located horizontally reads the coordinates of the drones in the swarm and the coordinates of the platform. The overall error of swarm formation landing was 4.2 centimeters in the case where each drone has a site. The better landing result was shown in the case where the leader drone is tracking in sightless drones. The average landing error in the leader-follower visual localization scenario is 1.9 centimeters. In this experiment, we tested 2 swarm landing scenarios on a moving platform. The landing platform was moving at a constant speed of 0.5 meters per second in a straight line. As the moving platform moves, the swarm of drones follows the robot trajectory from its initial positions without changing their landing formation by yawing until they land on the target location. The overall error for the swarm formation is 6.9 centimeters in the homogeneous swarm visual localization scenario, and 4.7 centimeters in the leader-follower visual localization scenario. In the last experiment, the drones landed on a platform moving along a complex trajectory with a constant speed of 0.5 meters per second in the leader-follower visual localization scenario, since it showed less landing error in the first 2 experiments. Since the drones followed the mobile robot along a complex trajectory for a long time and rotated along the z-axis to maintain their formation, in this experiment, the maximum error was higher than in the case of the stationary platform. However, the average positional error did not exceed 19.4 centimeters, which was considered as sufficient accurate by not exceeding the dimensions